Right, in this video, we are going to talk about static hazard and how to modify the circuit to get rid of the static hazard from the original circuit. Static hazard in combinational logic, right? It's caused by delay from the circuits. So let's take the example by using the 2-to-1 mux multiplexer. We introduced a couple of videos before. And so the logic circuit, the block circuit looks like this. It's 2-to-1. So you have I0, I1, and you have a Y here. It's a 2-to-1 mux, and you have a selection bit, right? And the truth table, the key map can be designed like this. So as you have 0, 1, I0, I1 can be 0, 0, 0, 1, 1, 1, 1, 0. And now let's take a look at the output here. And what are they? Okay. So that's a logic block, and that's a key map. So if when S is 0, right? When S is 0, we are picking up I0 to be delivered to Y. So which means you have let's I1, I0. So they are, that's MSB, that's a LSB. So when S is 0, you are picking up I0 to Y. So when I0 is at this bit, right, on the LSB, when that one is 1, you got a 1 for the output. So only for these two cases. So when S is 1, you are picking up I1. So I1 is right at here. See, on the MSB. Then, so when MSB is 1, you have a 1 for the output, right? And how to design the circuit? Apparently, you just group these two, and so you can get a logic expression which is Y equals to S bar, and this one got toggled, so you have only I0 left, and then S, which one is toggled? As I0 is toggled, you have I1 left. So that's a logic function for the 2-to-1 mux. However, if you only have this, you are going to have a static hazard. I'm going to show you what is a static hazard in the waveform. So for example, you have a circuit for this logic function, I0, S, I1, that's the 4 signal lines. And yeah, it's the same signal line, but I just draw it. Look, it's more clear for you guys. It's not being overlapped together. So I0 and S bar, so that's actually S bar, I0, S bar, you AND them together, and you got a signal called K0, and S and I1, you AND them together, you got signal K1, and then finally K0, K1, or together, you got a Y, which is the final result. And because of the natural property of the logic gates, they have capacitor, parasitic capacitors. Actually, we didn't cover that because it's a digital class. All these gates, they have oxide layer in the NMOS or PMOS. That's why you have dielectric material being introduced in between two metal plates, like the gate, oxide, and the silicon semiconductor. So you get a capacitor. But when you have a capacitor, you got a delay in time. So that's why we want to look at this kind of circuit, and we will take the delay into the consideration here. So for example, the inverter will introduce a 0.5 nanosecond delay, and the NAND gate will introduce a 1 nanosecond delay. It's the same AND gate, and OR gate will have a 1 nanosecond delay as well. And now we have a sequential our signal line. So I0 is always 1, I1 is always 1, for example, and we have our S, our selection signal, to be 1 at the beginning, and then being turned off for 1 nanosecond, and then being turned on. So what's the S bar will look like if you have your selection signal, being like that? because the inverter has a 0.5 nanosecond delay. And for example, this time period is 1 nanosecond. So your inverter will have a 0.5 nanosecond delay, which means in the beginning it's going to invert it. However, when this one changes, your inverted signal won't be changed immediately because you have a 0.5 nanosecond delay. So it's going to happen here, right in the middle, because the entire period here is 1 nanosecond. It's going to wait for 0.5 nanosecond and then start changed to logic high and then come back. So this entire signal does invert this signal, however, with a 0.5 nanosecond delay. So that's how that happens. And then we look at these signals and we'll think about what is a K0 and what is a K1. What are they? So now you can see that K0 is actually this signal. No, so here's still S, but here's S bar, right? So S bar is inverted, you get S bar. I'm sorry for that, there was a mistake over there just in the very beginning. Okay, so S bar and I0 and together we get a K0. Now we just look at this curve format here. So you have S bar, you have I0, you just add them together. Then you can have a signal K0. However, the final result will be a 1 nanosecond delayed. Okay, so now let's see. In the very beginning, 1 and 0, so it's going to be 0 until here. It should change immediately, but however, you have a 1 nanosecond delay. That's why this one will be delayed for 1 nanosecond, and you have a 1 1 happen afterwards. So you are going to have a 1 1, 1 logic 1 here, and then become 0 with a 1 nanosecond delay. Okay, after this. What about K1? So K1 is S and I1, but S is like that, I1 is like that here. So the only delay for these two signals and together is the AND gate. Okay, that's why you want to do it in the beginning. It should be 1 since 1 and 1 is 1 until here. You should have a 0 dip for 1 nanosecond, but actually it's going to be delayed for 1 nanosecond, and then you have this dip, 1 nanosecond dip. Okay. What about the final signal? Final signal is the OR logic with these two guys. However, you have a 1 nanosecond delay for the OR gate. So let's see. So you have a 1, 0 or 1 will be 1, 0 or 0 will be 0. However, it's going to happen 1 nanosecond delay, not here, but here. How long is that? It should be 0.5 nanosecond, right? And then you have 1 again, so you only have a 0.5 nanosecond dip for your final result. So that's the final result. However, the problem is when you have, because of the time delay, you have a little bit difference between these two signals. That's why it introduces a dip to here. However, you don't have that dip, you know. So which means when the signal is being changed from 0 to 1, right, or 1 to 0, 1 to 0, it jumped from here to here, and there's no 0 happens. It's always 1. However, because of the time delay, you're introducing a little dip into your circuit, so which is called static hazard, static 1 hazard. Why is a static 1 hazard? Because the state are being changed between ones. That's why it's a static 1 hazard. So the way to get rid of it is, let's just group them together. And then we are introducing another min term to the logic function, and we'll get rid of the static hazard. So what is that? So you are toggling S, so you only have I1, I0 here. So which means you want to add I1 and I0 and OR together in the very end, right? And OR to there, so you can get rid of that. That's the way we remove the static hazard. Now let's take a look. Why is that? Why is this gonna happen? So the reason, so when you are adding this to there, your when the state is being jumped from here to here, your I1, I0 are always ones. So which means I1 and I0 will be one all the time when you are changing this state. So you are introducing a logic 1 to the OR gate, which is a super strong logic 1 to holding. That result here will stay at 1 and won't be changed at all. I don't know if you get this. If you do not, replay the video again and see if you can understand this for the next time. So now let's see, let's repeat it, okay? So when the state is being jumped from here to here, if we don't group them, which means we didn't add this group to the circuit, and you get a little static hazard, which is a little zero dip in your final result. However, the way to remove it is to group these two to get rid of it. The reason you can get rid of it by grouping these two is when this state jumps to this state, you have your I1, I0 always be 1, right? So you just add it to there, so you can add a very strong logic 1 to the OR gate, which will hold it to be 1 all the time and won't let this dip happen, okay? And we're going to give you another example really quick for more inputs, and we'll do a really quick simulation to show you, the details about how we can make it work in that way, and it's going to be more intuitive. So let's do it. Now let's take a look at the example for identify static 1 hazard and static 0 hazard from K-map, and then try to fix it. So it is actually 8.2 example from the textbook. So the question is, identify 1 and 0 hazards design circuits without hazards. Okay, so here is a main term for the logic expression. You have 4 inputs and 0, 4, 5, 10, 11, 13, 14, 15. All right, so that's it. That's everything given to you, and you need to find out the static 1 hazard and static 0 hazard from the logic, and then try to fix it. So now let's take a look at that. A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and 0. So at 0 location, you have a 1 here, and 4 will be 0, 1, 0, 0, 5, 0, 1, 0, 1, 10, 1, 0, 1, 0, 11, 1, 0, 1, 1, 13, 1, 1, 0, 1. Is that 1, 1, 0, 1? Plus 5, yes. So 1, 1, 0, 1. 14, 1, 1, 1, 0. 15, 1, 1, 1, 1. Okay. This, and now you got hazards here. All right. So there's a static 1 hazard, static 1 hazard, right? So design the circuit without the hazard, you just group these ones as well. So get rid of the issue. So finally, so in the beginning, right? So in the beginning, you have not y, it's called f. So the original logic function here is a bar, c bar, d bar, right? Because b is toggle, so just can't ignore that. Or b, c bar d, or these four, a, c, okay? That's a circuit with the hazard. And you want to get rid of the hazard, add two more terms. This group here, these two, which is a naught b and c naught, or these two, a b and d, right? So that's a circuit without hazard. Right. So now we get rid of the static 1 hazard. What about the static 0 hazard? Okay, so when you are designing using the max terms to make up a circuit, you will have static 0 hazards. So now let's get rid of the 0 hazards as well. So the same K-map. And you know there are ones at these locations, so zeros will be at the rest of the locations. So you have 0 here, 0 here, 0 here, and you have 2 zeros this row, and then 1 0 for this row, and 2 zeros here. Okay, so now let's start group all these things. One group, one group, one group. And you find out there are two static 0 hazards, this one and this one. So just group them so you can get rid of the static 0 hazards. So in the very beginning, your logic function, sorry, A, B, C, D is, so now max terms, right? So don't forget to swap it. So now you have A, you have B toggle, so A bar or wait, yeah, this one, C or D, right? That's the first max term. And this row, you have which one toggle? A toggle. So B is B because it's 0 here. In the max term, you just keep it as B when you see a 0 here. And or C or D bar. And one more here. It is A or C bar. Okay, that one has zero static hazards. And you are, so we had a conclusion from the very beginning from the 2-to-1 mux example, and we know that when you have adjacent cells, are not being grouped together, then you are going to have a hazard. So that's why you want to group them together to get rid of the hazard. So now we just, put all this maximum over here. So we are going to have hazards. That's why you need to add a few more terms for these parts, these two groups. So for this one, you are going to have A bar or B and or C, and these two will be A or B or D bar. Okay, so that entire thing doesn't have static zero hazards. Okay, that's how to do it. All right. Yeah, I don't think we have time to do the simulation, but so we are running the simulation. You want to recover that static hazards. You can refer to the first example on the first page. We have this part, and you just have this kind of sequence over here. You should be able to see that little glitch, and you can remove it by adding a part to it, so you won't have that static hazard anymore. Okay, this is how you do it. And now I think that's everything about static hazards, and you just go ahead and do the homework. Again, if you have questions, welcome to send me an email or ask me questions during the office hours. So thanks for watching. I'm gonna see you in the next video. Okay.